Albert Einstein once asked a question that sounds like it belongs in a mental asylum, but was actually asked in the halls of the most prestigious university in the world. He turned to a colleague, pointed out the window, and asked, "Do you really believe the moon is not there when you are not looking at it?" It sounds ridiculous. Of course, the moon is there. The world is solid. The chair you are sitting on is real. Your phone is real. If you close your eyes, the world doesn't vanish. Reality is not a video game that only renders what is on the screen, right? But for the last 100 years, physics has been trying to tell us something that we really do not want to hear. Physics is trying to tell us that Einstein was wrong. We have discovered a crack in the foundation of the universe. A place where the rules of logic dissolve. A place where things can be in two places at once. A place where the past can be changed by the future. And a place where reality doesn't seem to exist until you force it to. This isn't magic. It isn't philosophy. It is the most tested, most verified, and most accurate scientific theory in human history. It is the science that allows your computer to work, your GPS to navigate, and the sun to shine. It is called quantum mechanics. And at the heart of it lies a concept so strange that it drove the men who discovered it to the brink of madness. It is the concept of superposition. You have probably heard of Schrodinger's cat, the cat that is both dead and alive at the same time. You've probably laughed at it. You've probably thought it's just a funny metaphor, but it is not a metaphor. It is a description of you. Right now, the atoms in your body are obeying rules that defy common sense. Today, we are going to stop pretending that the universe makes sense. We are going to dive into the microscopic abyss. We are going to look at the experiment that broke reality. And we are going to try to understand why the universe is waiting for you to look at it. Chapter 1. The War of Light, the Double Slit. To understand the madness, we have to start with something simple. We have to start with a beam of light. For centuries, scientists fought a war over what light actually was. On one side, you had Isaac Newton. He said light was made of particles, tiny little bullets. This made sense. Light travels in straight lines. It bounces off mirrors like a ball bouncing off a wall. On the other side, you had the wave people. They said light was a ripple, like sound or water. In 1801, a man named Thomas Young decided to settle the argument. He designed an experiment that is now the most famous experiment in the history of physics, the double-slit experiment. It is deceptively simple. Imagine a wall with two vertical slits cut into it. Behind that wall is a screen. Now, imagine you have a machine gun. You fire bullets at the wall. Some bullets hit the wall and stop. Some go through the left slit. Some go through the right slit. On the back screen, you would expect to see two bands of bullet holes. Left band, right band. Simple. This is how particles behave. Now, imagine you put the whole thing in a swimming pool. You send a wave of water at the slits. The wave hits the wall. It squeezes through both slits. On the other side, the two new waves crash into each other. Where the peak of one wave meets the peak of another, they get bigger. Where a peak meets a trough, they cancel each other out. This creates a pattern on the back screen called an interference pattern. It doesn't look like two bands. It looks like a barcode. Band, gap, band, gap, band. So Thomas Young fired light at the two slits. And on the back screen, he didn't see two bands. He saw the barcode. He saw the interference pattern. The debate was over. Light behaves like a wave. Newton was wrong. Everyone went home happy. But then, 100 years later, the nightmare began. We started looking at matter. We looked at electrons. Electrons are the building blocks of the universe. They are the tiny rocks that make up reality. They have mass. You can count them. They are definitely particles. They are tiny bullets. So in 1927, physicists Davison and Germer fired electrons at a double slit. They expected to see two bands. They expected the electrons to act like tiny marbles. But they didn't. On the back screen, the electrons formed an interference pattern. The rocks were behaving like water. This was a catastrophe. It's like throwing bowling balls at two open doors and watching them turn into a liquid, wave through the doors, and then turn back into bowling balls on the other side. It shouldn't happen, but it gets worse. The scientists thought, okay, maybe the electrons are bumping into each other. Maybe the crowd is creating a wave, like water molecules. So they decided to fire the electrons one at a time. Click. Click. One single electron travels through the experiment. It has nothing to bump into. It is alone in the universe. It has to choose left slit or right slit. They let the experiment run for hours, firing one by one, building up the image on the back screen dot by dot. When they developed the picture, they stared in horror. The interference pattern was still there. Do you realize what this means? It means the single electron left the gun. It arrived at the wall. And then, somehow, it went through the left slit and the right slit at the exact same time. It interfered with itself. It crossed its own path. And then it landed on the screen. The electron wasn't a particle, and it wasn't a wave. It was a ghost. Chapter 2. The Wave of Possibility. Schrodinger's Equation. Physics was in crisis. The old rules classical mechanics said that a thing is always in a specific place at a specific time. But the experiment proved that a thing can be in many places at once. Enter Erwin Schrödinger. Schrödinger was an Austrian physicist. He was a passionate, philosophical, and somewhat eccentric man. He hated this ghost idea. He wanted to bring order back to the universe. He sat down and wrote an equation, the Schrödinger equation. It is the most important equation in quantum mechanics. It describes how these tiny particles move. But to make the math work, Schrödinger had to accept something radical. He realized that you cannot describe an electron as a point in space, XYZ. You have to describe it as a wave function, represented by the Greek letter psi, dollar, psi dollar. But what is this wave? Is it a wave of energy? Is it a wave of electricity? No, it is a wave of probability. This is the core of superposition. When the electron is traveling through the dark, unobserved, it does not have a position. It is not here or there. It exists as a cloud of possibilities. It is 50% likely to be in the left slit. It is 50% likely to be in the right slit. And until it hits the wall, it is literally in both. It is superposed. Think of it like a ripple on a pond. The ripple isn't in one spot. The ripple is the whole pond. The electron is a ripple in the fabric of reality. This was a profound shift in how we understand existence. Before this, we thought the universe was deterministic. We thought that if you knew the position of every atom, you could predict the future perfectly. Schrödinger showed us that the universe is probabilistic. At its core, reality is fuzzy. But Schrödinger himself was uncomfortable with this. The math worked, but the implications were insane. If an atom can be in two places at once, and if we are made of atoms, ... why can't we be in two places at once? Why don't we see chairs blurring into different locations? Why don't we see people walking through two doors simultaneously? Why does the quantum world look like a hallucination, or the macro world look solid? This brings us to the biggest mystery in science, the mystery that keeps physicists awake at night, the measurement problem. Chapter 3. The Eye of the Observer. Let's go back to the double-slit experiment. The scientists were baffled. The single electron was going through both slits. It was superposed, so they decided to get clever. They said, let's catch it in the act. They placed a sensor detector right next to the slits. They wanted to see which slit the electron actually went through. They wanted to spy on nature. They turned on the machine gun. They turned on the sensor. The first electron came. The sensor went beep it, saw the electron go through the left slit. The next electron came. Beep right slit. The sensor worked perfectly. It tracked every single electron. 100% left or 100% right. No ghost stuff. But then they looked at the back screen. The interference pattern was gone, replaced by two boring bands. The moment they looked, the wave vanished. The electron stopped behaving like a ghost and started behaving like a bullet. It stopped going through both and chose one. This is called the collapse of the wave function. When you aren't looking, the system is a wave of infinite possibility. When you look, measure, the system snaps into a single reality. This result is so disturbing that, for decades, people refuse to believe it. Does the electron know it's being watched? Is it conscious? Does nature hide its secrets when we try to peek? This is where the New Age mystics jumped in. They said, consciousness creates reality. Your mind controls the universe. But physics is colder than that. It's not necessarily about a human eye. It's about interaction. To see an electron, you have to bounce a photon, light, off it. That photon hits the delicate quantum system and disturbs it. It pops the bubble. But the mystery remains. Why is the bubble there in the first place? And where do all the other possibilities go when the bubble pops? This is the tension that Erwin Schrödinger wanted to expose. He saw that his fellow physicists, specifically Niels Bohr and the Copenhagen interpretation, were accepting this too easily. They were saying, the particle has no reality until you measure it. Schrödinger thought this was stupid. He wanted to show them just how absurd it was to apply these quantum rules to the real world. So, in 1935, he came up with a thought experiment. He wrote a letter to Albert Einstein. He said, imagine a cat. He didn't mean it as a serious scientific proposal. He meant it as a joke. He meant it as a reductio ad absurdum, an argument designed to show that a theory leads to a ridiculous conclusion. He tried to invent the most ridiculous scenario possible to mock quantum mechanics. But ironically, the joke backfired. The joke became the most famous teaching tool in physics. He put the cat in a box. And he armed a Bond chapter for the zombie cat Schrodinger's thought experiment. So, let's open the box. Erwin Schrödinger wanted to prove that the idea of superposition was nonsense when applied to the real world. He wanted to show that a cat cannot be dead and alive at the same time. Here is the setup he proposed in 1935. It is a Rube Goldberg machine of death. You take a steel box. You put a cat inside. Along with the cat, you put a tiny amount of radioactive material, so small that in the course of 1 hour, there is exactly a 50% chance that one atom will decay, and a 50% chance that it will not. If the atom decays, it triggers a Geiger counter. The Geiger counter releases a hammer. The hammer smashes a vial of cyanide poison. The cat dies. If the atom does not decay, the hammer stays put. The cat lives. You seal the box. You wait 1 hour. Now, according to the rules of quantum mechanics, the Copenhagen interpretation, until you measure the atom, it is in a state of superposition. It has decayed, and it has not decayed. It is a wave of both possibilities. But because the cat's life is linked to the atom, the cat enters the superposition too. Until you open the box to check, the mathematical equation describes the cat as live cat plus dead cat. Schrödinger said, this is absurd. He knew that if you opened the box, you would never see a blurry, half-dead ghost cat. You would see a living cat, meow, or a dead cat, thud. He argued that reality must choose a state before we look at it. But history played a cruel joke on Schrödinger. Instead of killing the theory, His example immortalized it. Physicists realized that, mathematically, he was right. As long as the box is perfectly sealed, no information leaking out, the cat is fundamentally undefined. The universe does not have a truth about the cat until an interaction forces it to decide. This leads to a terrifying question. Who opens the box? If the cat is in superposition until I look at it, am I in superposition until you look at me? Is the entire universe just a nesting doll of boxes, waiting for a godlike observer to look at the whole thing and make it real? This question drove physicists into a corner. They had two choices. Choice A, accept that collapse is a magical event where possibilities vanish and only one truth remains. A Copenhagen interpretation. Choice B, accept that the possibilities don't vanish. They just go somewhere else. This brings us to the most mind-bending theory in all of science. A theory that was ridiculed for decades, but is now accepted by many of the world's top physicists, including Sean Carroll and David Deutsch. The Many Worlds Interpretation. Chapter 5. The Splitting of the Universe in 1957. A doctoral student at Princeton named Hugh Everett III had a radical idea. He looked at the math of the Schrödinger equation and said, what if the wave function never collapses? What if the electron doesn't choose left or right? What if it does both ... But in different worlds? Everett suggested that every time a quantum event has multiple possible outcomes, all of them happen. But they cannot happen in the same timeline. So the universe splits. Let's go back to the box. You stand in front of the steel box. You are about to open the lid. In Everett's view, there is no 50% chance. There is 100% certainty that the atom decays, and 100% certainty that it doesn't. At the moment of interaction, reality branches. In Universe A, you open the box, you see a live cat, and you feel happy. In Universe B, you open the box, you see a dead cat, and you feel sad. Both versions of you are equally real. Both versions feel like they are the true you. Both versions possess a continuous memory of the past. But they are forever cut off from each other. They exist in parallel, decoherent branches of reality. This is the multiverse. And it isn't just happening with cats. It is happening with every electron, every photon, every collision in your body. Billions of times a second, the universe is fracturing into infinite copies. There is a world where you didn't click on this video. There is a world where you became an astronaut. There is a world where the asteroid missed the Earth and the dinosaurs are still here. This theory solves the measurement problem because it removes the observer. You don't create reality by looking. You just find out which branch you are on. But it introduces a new kind of horror, quantum immortality. Imagine you play Russian roulette with a quantum trigger. In 50% of the universes, the gun fires. In 50%, it clicks. From the perspective of the you who dies, the lights just go out. The consciousness ends. But from the perspective of the you who survives ... you hear a click. You pull the trigger again. The universe splits again. Half of you die. Half of you survive. The survivor consciousness continues. To an outside observer, you will eventually die. But to yourself, you might experience a freakish streak of luck where the gun simply never goes off. You are trapped in the timeline where you survive. This is pure speculation, of course. But it highlights the disturbing nature of the many worlds theory. It suggests that everything that can happen does happen. We are just surfing one single wave in an infinite ocean of events. Schrödinger hated this. Einstein hated this. But do you know who loves this? Computers. Chapter 6. Harnessing the Ghost, Quantum Computing. For 80 years, all of this superposition, entanglement, many worlds, was just philosophy. It was guys with chalkboards arguing about the nature of truth. But in the 21st century, we decided to stop arguing and start building. We realized that if an atom can be in two states at once, we can use that atom to do math. This is the birth of the quantum computer. Here is how it works. Your laptop, the one you are using right now, runs on bits. A bit is a switch. It is either 0 off or 1 on. Everything you see, Netflix, YouTube, video games, is just a massive stream of O south and 1 south. If you want to solve a maze with a classical computer, it has to try every path one by one. Try left, hit a wall, return. Try right, hit a wall, return. It is fast, but it is sequential. A quantum computer uses qubits, quantum bits. A qubit is like a spinning coin. While it is spinning, it is not heads, 0, and it is not tails, 1. It is a blur of both. It is in superposition. This allows the quantum computer to try every single path in the maze at the exact same time. Imagine you have a library with 1 billion books, and you have to find one specific sentence. A classical computer has to read book 1, then book 2, then book 3. It takes 1,000,000 years. A quantum computer walks into the library and reads all 1 billion books simultaneously in a single instant. This isn't just a faster computer. It is a different kind of machine. It is a machine that thinks in parallel universes. Right now, companies like Google, IBM, and nations like China and the US are in an arms race to build these machines. Why? Because a working quantum computer can break every password on Earth. Encryption relies on math problems that are too hard for classical computers to solve, like factoring massive numbers. A classical computer would take the age of the universe to crack your bank password. A quantum computer could do it in minutes. But it can also do miracles. It can simulate molecular bonding to invent new medicines that we can't discover today. It can model the climate perfectly. It can design new materials. We are taking the ghost, the weird, spooky, impossible superposition, and we are putting it to work. We are turning the glitch of the universe into the engine of the future, the reality of uncertainty. So, where does that leave us? We started with a beam of light. We ended with the splitting of reality. What does Schrodinger's cat actually teach us? It teaches us that our intuition is a lie. We evolved on the African savanna to hunt gazelles and avoid lions. We evolved to understand rock is here and tree is there. We evolved for certainty. But the universe is not certain. At its foundation, the universe is a shimmering, vibrating cloud of probability. Nothing is fixed until it interacts. This might make you feel small. It might make you feel like nothing is real. But I think it is liberating. In a deterministic universe, Newton's universe, the future is already written. The atoms were fired at the Big Bang. And everything that happens, including you watching this video, was calculated 13 billion years ago. You are just a cog in a clock. But in a quantum universe, the future is not written. The future is a superposition. It is a cloud of infinite possibilities, waiting for an observer to collapse them. You are the observer. Every choice you make, every interaction you have, collapses a wave. You are constantly navigating the branches of the multiverse, forcing the fuzzy potential of tomorrow into the concrete reality of today. The cat is not dead. The cat is not alive. The cat is waiting for you to open the box. So ... What are you going to choose?